So here's our last video dealing with parametric equations, which we're going to talk about the second derivative, which has a little bit of a quirkiness to it. I'm going to start by sounding very much like Calc 1, right? This notation is always interesting. Everybody thinks I'm making a typo, but this is how you write the second derivative. And the way I interpret it is you're taking the derivative twice of the y variable with respect to x twice. So that's kind of the meaning behind that notation. Now, from Calc 1, you definitely saw this notation for sure, and it was basically like, hey, take the derivative with respect to x of dy dx. You know from Calc 1 that the second derivative is just take the derivative again, right? That's pretty much all it is. The problem in the parametric setting happens to be the variable issue again. Keep in mind that dy dx really is in terms of t. That's what causes us a little bit of an issue on the second derivative defined parametrically. So here's what I can do. When you think about like, well, I'm going to have dy dx, right? Let's even just go back to that last example. Dy dx was 6 square root t. I can take the derivative of this, no problem. Like, sure, no problem at all. But when you're taking the derivative, you're taking the derivative with respect to t. So let's be clear about this. I'm going to take the derivative with respect to t of dy dx, because that's all I can do. But you see how I have a variable problem here. Right now I have d squared y over dt dx. That's not what I want. I want d squared y over dx squared. So I'm going to make it work just by doing this. That will create the notation that I'm looking for, because in this moment you can see how, oh, well, that's nice, the dt's kind of cancel, and that will leave me with d squared y over dx squared. This is great, okay? So a little bit of a quirky notation issue happening here. And let's describe what this actually is. I can say, look, let's take the derivative with respect to t of dy dx. That's doable. Multiplying by dt over dx is the same thing as dividing by dx dt. This is what I need to have happen. This is the way it pretty much looks in practice. So let me talk this out for you. This is what you need to remember in terms of like, what is the formula for taking the derivative, the second derivative, parametrically. That's it. Let's talk about what that actually means. So I'm going to write it in words, which is interesting. But what I want you to do is say, look, the second derivative parametrically means take the derivative of the first derivative with respect to t. So do as you normally would. Take the derivative of dy dx. But remember I said the parametric second derivative has a little extra. See this guy down here? That's your old dx dt. So I'm actually going to write it like that. The extra here is make sure your denominator has the old dx dt expression in the denominator. It needs to be there. That's what I'm saying. It's a little bit quirky. So your second derivative parametrically is not simply, oh, just take the derivative of the first derivative. You do. You do that in the numerator, and then you make sure in the denominator you have your old dx dt. That's the extra. And that's what I really need to focus on, that you don't forget to do that. Everybody forgets, and I don't want you to forget. It's the whole point of asking for the second derivative. So let's go through and do some of these problems here. Example 6, we've got ourselves a set of parametric equations where our parameter is theta. We're back in trig land. So no problem. They want me to find the second derivative, the value of the second derivative at theta equals pi. And then we'll describe concavity. So we'll talk a little bit of meaning about that second derivative. So let's go ahead and get in there and get started, which means I need to find first dy dx. Now, our parameter is theta. Notice, again, they define the x equation first and the y equation separate. But when I do dy dx, I want the derivative of y in the numerator. So the derivative of 1 minus cosine is positive sine. And the derivative of x in terms of theta would be 1 minus cosine. So that's great. Now, I want to move on to doing the second derivative, and I'm going to utilize my strategy here. I am going to take the derivative of the first derivative. I actually think I might need a little bit more space there. So I'm going to do the derivative of the first derivative up here. And then I'm going to put it over the old dx dt. The old dx dt is that denominator you had here. That's dx dt is the derivative of x. So I'm going to do that. My old dx dt, don't forget about it, is 1 minus cosine. I usually start by writing that because I don't want to forget about it. Now, what am I doing in the numerator? Well, the numerator is, hey, take the derivative of dy dx. Well, that's right here. I'm going to do a quotient rule. I feel like that's the easiest thing to do here. So this looks a little messy. We're going to get in here. We're going to do it. The quotient rule, it's always bottom times the derivative of the top minus the top times the derivative of the bottom. The derivative of 1 is 0, and the derivative of negative cosine would be positive sine. And I put it over the bottom squared. That looks like an absolute mess. So I'm going to clean it up. I promise, promise, promise. So let's do that. Let's pay attention to that numerator. I'm going to distribute that cosine in there. So I'm going to say 1 times cosine is cosine. Then I have cosine squared, and then I have sine squared. Now, what do I have going on? Well, okay, you have this expression divided by 1 minus cosine. Okay, let me write it like this so I don't lose anybody. I'm going to take the top fraction and instead of dividing that 1 over cosine, let's think about it like this. Let's think about it as multiplying by 1 over 1 minus cosine. That's what you do with a complex fraction. We want to get rid of that fraction and a fraction. So let's play around with this. What that means is my denominator is actually 1 minus cosine theta cubed. And I can actually clean up this numerator if you want to and like make this a lot nicer. I'm going to do a little bit of fancy trig work here. Well, not really. I'm factoring out a negative. Notice how that changes the sign. In here, this is now cosine squared plus sine squared. That is that identity that I referred to in the very last video, I think. Or maybe the one before that, where cosine squared plus sine squared is 1. I probably wrote sine squared plus cosine squared is 1. Guess what? It doesn't matter. Order doesn't matter. This is addition. So your second derivative here can be written like this. Cosine theta minus 1 over 1 minus cosine theta cubed. So let's now answer the question. Like, this is what the second derivative is. I can carry my notation down, I suppose. Okay. They asked me, hey, what's the value of the second derivative at pi? Let's do it. D squared y over dx squared evaluated at pi is going to be, well, cosine of pi minus 1 over 1 minus cosine pi cubed. So cosine of pi is negative 1. And so I would have negative 2 over 8. And my answer to that second derivative is negative 1/4. Now, the meaning here, they wanted me to connect this with concavity, so I'll do that here at the last statement here. You know from Calc 1, if your second derivative at a location is negative, your graph at that moment is concave down. So I'm just going to say the graph is concave down at theta equals pi, since the second derivative has a value that is greater than 0. Oh, I'm sorry. It's concave down because your second derivative is less than 0. Oh, my goodness. There we go. Concave down. There's your correct justification. All right. And so here we go with our last example here. Putting a couple of these things together with everything that we've talked about with calculus, first derivative, second derivative, old school calculus, new school calculus. So here's our set of parametric equations, and we are going to write the equation of the line tangent to the curve at 2, -4. So this is pretty nice in the sense that, like, look, I always need 3 things to write the equation of a tangent line. I need an x-coordinate, which they gave me, and a y-coordinate, which they gave me, and a slope, which I now need to figure out. The slope is going to be the value of dy dx. I just have to know where to evaluate it, because I'm in the set of parametric equations. I've got to know the t value that I'm interested in. So let's kind of figure it out. Let's see what dy dx is, right? I'm just going to do dy dx over here. Dy dx is the derivative of y over the derivative of x. And I might as well clean that up to make it friendlier for me. So I've got an expression for dy dx, but I don't know what to plug into that derivative. The dy dx is in terms of t. I don't have t. I know that x is 2. I know that y is -4. So let's see what we can do. Let's actually take a look at this and say, all right, well, if x is 2, right? Let's see what happens. 2 must equal 2t squared. Let's see if we can figure out what t is from here, just algebraically. I can divide by 2 on both sides, and I can solve for t. Now, when I take the square root, I need a plus and a minus in here. So I'm actually not sure what t is. Is it +1 or is it -1? Algebraically, I'm not sure. And I have to pick the right one. Okay, so let's think about it. Let's come in here and say, all right, if, change colors, so I'm thinking about this. If t equals 1, then y equals 3 times 1 cubed minus 1. That's just my rule for y. I'm just going back up here and like playing around with it. Like if t is 1, I already know that t is 1 would give me that x is 2. But unfortunately, it tells me that y is 2, and that's not what I see on my ordered pair. So that's not right. So that must mean that t is -1. Let's check it out. If t is -1, 3 times -1 cubed minus 1, what does that give me? Yeah, that's -3 minus 1. That's it. So now I know what to plug in. I had to make a choice logically about which one it is, and so turns out I'm going to be plugging in -1 for t, so I can come back over here, and now I know what to do. I now know that I'm going to plug into that derivative, so I'm just going to do 9 times -1 over 4. And those are the 3 puzzle pieces, right? I needed an x value, a y value, and a slope. I'm well on my way to writing the equation of the tangent line, and so I'll do that here. Y minus -4 is y plus 4. There's my slope. There's my x value. You can solve. This is great. This is great. Sometimes the question will ask you to put in slope-intercept form, and so you would just convert it over, and so here is my equation in slope-intercept form. I accept both of them. Look and see what WebAssign would like you to respond. If they ask you this question at all, maybe they'll just ask you for dy dx, and your answer is -9/4. Okay. What I want to do is compare this with part B. This one is sort of the opposite scenario. In part A, you were given the x and the y, but not t. All right. Now, I want to be clear about what's happening here. Here, you're given the t. Like, what I don't know is I don't know x and I don't know y. They did not give that to me. But I know I can do the derivative real nice because I'm supposed to be plugging in 2. They told me to. So great. Let me use that derivative. It's the same derivative, right? Your derivative is going to be, let's see, 9 times 2 over 4. And so what does that 9 have? So in this part, I've got the slope really quickly, but I don't have the x and the y. No problem, because you were given the equation here of the set of parametric equations, and so I'm just going to plug in. If t is 2, that means x equals 2 times 2 squared, otherwise known as 8, and y is 3 times 2 cubed minus 1. That gives me 3 times 8, which is 24 minus 1, 23. So cool, I can write the equation of the tangent line here. I've got y minus 23 equals 9 halves x minus 8. That's great. That's point slope form of a line. Check and see. Sometimes you may need to convert it to slope intercept form of a line, and here's what I would end up with. Okay. All right. So, marrying all of this together, we're finally going to talk about the second derivative here, because in part C, they're asking you that concavity question. Is it concave up or concave down? Well, that's dependent on the second derivative. So we will work on evaluating that second derivative. Let me use the notation, and let me start out by saying, look, I am going to do the derivative of dy dx in the numerator, but I am going to make sure I put it over the old dx dt. So let's go back and look at what x is. Remember, x is 2t squared, and so the derivative of 2t squared is 4t. That's what I'm putting here. I don't want to forget it. That's why I do it first. In the numerator is where you're going to say, hey, just take the derivative of the first derivative. And the first derivative was 9t over 4. So that derivative is 9/4. Now, I am going to take the top fraction and multiply by the flip of the bottom fraction. That is your second derivative. Now, they're asking me about concave up or concave down, and they specifically said, hey, at t equals 2, well, let's evaluate the second derivative at t equals 2, and I end up with 9 over 32, which is positive. So I'm going to say, therefore, that's what those three dots mean, the graph is concave up at t equals 2. I already justified it because I said, hey, it's because the second derivative is positive. So I've got that justification already down. So I just want to be clear. Your justification is the statement of, hey, the second derivative is greater than 0. You actually came up with the value, and you showed that it was greater than 0. Okay, so that wraps up Unit 2. All our applications of area, volume, and this discussion of our new way of graphing with parametric equations.